Okay, now let's take a look at how we do interpretations for the Pearson R. So, a linear correlation coefficient measures the strength of a linear relationship between the paired values of x and y in any sample. So this is what the Pearson R does. Now, when we're interpreting it, we are two things we need to pay attention to in our Pearson R value. So, the value of the R indicates the strength of the relationship. The symbol indicates the direction of the relationship. So let's take a look at some examples of these and break these down. So the value of the R indicates the strength of the relationship. So the higher the level, the number in R, the stronger the relationship. If I have a positive symbol before my R, if I have a positive R, that means that as one variable is increasing, so does the other variable. Or in reverse, as one decreases, so does the other. A negative value for my Pearson R means that the values of x and y are the inverse of each other. So that means as one is increasing, the other is decreasing. Let's take a look at some examples. So here, if we take a look at this right here, we see our R is 0.851. So that makes it a positive. First of all, it's a strong relationship with a 0.85, because keep in mind, 1 is a perfect correlation and 0 is absolutely no correlation whatsoever. So if we're looking at this, notice that as my values go up on x, see where I've drawn the two red lines for the one data pot? Notice that as my x is increasing, right? So as I'm going from my red line over to my yellow line where my values of x are increasing, notice that the data point is further up the graph for that, right? Notice that my y values do the same. As they are increasing, it is also going up the graph. This is very different than this particular one right here, where we can see, again, we have an R of negative 0.965. So if we're looking at this, you can notice that as my elevation goes up, my x value from 1,000, say, to about 1,600, notice that the corresponding value for the mean annual temperature is going down. Thus, as elevation goes up, temperature goes down. That makes it a negative relationship. So make sure you're taking your time to work through these. Go back and watch them again if you need to make sure you have that clear for yourself before you proceed forward. So here, if we're looking at this, now if we're looking at this one, so we have a negative 0.0186. So this is, again, a negative correlation, which means that as the one variable is increasing, the other is decreasing. It's a pretty small correlation, though. So notice that the value there, 0.0186, that means there's not much of a relationship between these two different values. And indeed, you can see that when you're looking at it, both in terms of where the data points are kind of scattered around, and also you can see where they've plotted the line that would be for the linear relationship line. And you can see it's relatively flat. So before you do a correlation, here's several requirement checks you need to make. You need to make sure you have a simple random sample of quantitative data, as we have always done before. Each observation or participant should have a pair of scores. This is really important. You cannot have missing data. I cannot be running correlations if I have one value but not the other. This is actually a really common problem in real life where you're assessing data. Say, for example, I'm having people complete a set of scales that I want to analyze their data for. And if somebody has completed 3 scales but left out another scale and didn't complete it at all, I may have to actually take out all of their data because I can't do the analysis because I'm missing one of the pieces I would need. So we have to have these values, 2 values for each observation or participant. We also have to be aware that correlations are very sensitive to outliers. So an outlier is generally a score that is plus or minus 3.2 standard deviations from the mean. So that is considered an outlier. It is way outside, as we've been looking at with our empirical rule, right? So that would be outside the 3 standard deviations that we've been looking at with the empirical rule. One can remove outliers from the data if you have a database reason for removing the outliers, but you cannot remove them just because they're an outlier. So if I had reasons to believe that particular individual scores were in fact not indicative of them at all, let's say I found out that 3 of the people out of 400 people, when they were doing a particular assessment, there was, say, a practice emergency response to get out of the building due to a practice fire alert in the middle of what they were doing for their test, or perhaps like right before. So it was very disruptive. So I might choose to take those 3 people's data out, but that would have to be based upon how the data was collected and other reasons, not just because they're outliers. And lastly, when we're looking at correlations, linearity, it has to be a straight line.